All right, I apologize for breaking this up at such an awkward moment. I'm in my office and I needed to address something. So anyway, where were we? We were solving this differential equation using the method of separation of variables. So we were at this point where we had done we've done all the calculus up to here. Now we just want to solve for p. What is this function p? And I'm going to do some things where I'm a little bit loose, and I'll tell you, you can get away with that. So here, we had this plus c, I divided by 2, and I continued to call it plus c. Now, we know what the natural log of the absolute value of p is. So, at this stage, we want to get p by itself. What cancels a natural log? E to a power. So we can say e to the power natural log of the absolute value of p is e to the 1/2 t plus c. Now, I'll just tell you straight up, if you're not comfortable with exponent rules, you're not going to be able to finish these problems. When we add in an exponent, that's the same as multiplying two different exponential expressions with the same base. And I'm going to cheat again. I'm going to cheat again where I'll say that this thing here is e raised to some power, but I don't know what it is. So this is still kind of up in the air. If you're really careful, you might notice that it's positive. Don't stress over that. But the idea is this is some constant, and we really don't know much about it. So we can continue to say, all right, if it's just some constant and we don't know much about it, that's c. So here, this simplifies, right? E to a power and natural log cancel. That gets down to the absolute value of p. I'm just going to switch the order over here. Well, if the absolute value of p is this thing, then p, right, so think of just as an example, if I told you the absolute value of p is 5, that means p is plus or minus 5. Those are the two things that give you 5 when you take the absolute value. So what that means over here is we could say p is plus or minus c e to the 1/2 t. And again, we'll say, all right, c is some constant. And like, oh, but maybe I'm taking the negative version. All of this is still just some unspecified number. So we can feel like the uncertainty over plus or minus gets absorbed into the uncertainty as to what the heck c was in the first place. So our general solution here we can just say is c times e to the 1/2 t. And we might want to write it as p of t to emphasize that it's a function of t. So there are a lot of steps here. Make sure you go over them. This is our general solution. To find our particular solution, we will use this piece of information. P of 0, well, if I follow this, P of 0 will be c times e to the 0. E to the 0 conveniently is 1. So that's c, but we're told that that's equal to 50. Again, plugging in 0 often does really nice things for us. So our particular solution is p of t is 50 times e to the 1/2 t. So there's a lot of stuff going on here. A couple of notes. So very often there are tons of problems that involve integrating with 1 over x. That introduces a logarithm. So in order to do the other steps, you must be comfortable with log and exponential rules to finish. Right? If you feel like you're rusty on those, ask me for some help. Right? That also explains why this goes to explain why so many growth problems involve E. We don't realize it, but this is saying something about rate of change. It's saying something about growth. It turns out that when we say things like this about growth, we wind up integrating something like a reciprocal. That puts a log in the answer, and that eventually puts an e in the answer. So if it feels so mysterious, why do all these formulas that explain how things change over the time have e's in them? It has to do with this process. The integral of 1 over x is the natural log of the absolute value of x. Remember the absolute value, there's a plus minus. Sometimes the plus minus gets absorbed into a c so you can forget about it. Sometimes it will not, and you will see a plus minus in the answer. As you notice that I did here, it's okay to rename your arbitrary constant c as long as it appears only once in the equation. If you have it showing up in multiple places, be super careful. So if you have x plus c and you want to multiply by 2, you can call that 2x plus c. If it seems like you're not integrating anything, you're actually integrating 1. We saw that here. I actually want to make a general point here. So I'm going to improvise and add something. What we saw here is what's known as proportional growth. So I'll just point out this is a problem that we just did. We had dp over dt was 1/2 p. P of 0 is 50. And our particular solution was p of t is 50 times e to the 1/2 t. It might feel like, oh, I see where the 1/2 went and I see where the 50 went. This is an example of proportional growth. Proportional growth is when the rate of change is in proportion to how big the thing is. How fast is p growing? Well, the rate of change is exactly 1/2 of p itself. That's proportional. And proportional growth is exponential growth. Slash dk if I want to add this on either side. So in pre-calc, if you had a whole section where you did exponential growth and decay problems and you thought, why do all these problems involve e? It has to do with what we just saw. So to be very general, in general, if I have something growing in a way where it's the multiple k times p, the general solution, and it's okay if you just know this pattern. I want you to understand all the steps that I just went through, but also I want you to know proportional growth has a formula that looks like exponential growth, and whatever the constant of proportionality was, that same number shows up in the solution. And then the particular solution, the constant would just be however much we started with. So this is worth knowing. This is mentioned in the AP curriculum. Yes, they want you to be able to solve this step by step, but they also want you to just plain know how it's supposed to work out. This could be a multiple choice problem where they're not expecting you to spend 4 or 5 or 6 minutes going through all the steps that I did up here. They're expecting you to know the pattern, right? So you should just know that if I tell you y prime equals 3 times y, you instantly know, oh, this is proportional growth. It's saying the rate of change is 3 times the function. What kind of function does that? Some constant times e to the 3x. The constant 3 shows up as a coefficient in the exponent. But when the rate of change is a multiple of the function itself, we get exponential growth like this. It's a shortcut that you should know. But going back to what I have here formally, so take some more time and try these. Find the general solution based upon the differential equation I'm giving you, then try to find the particular solution. So hit pause and give those a shot. Okay, so let's take a look here. So here I have dy over dx equals y squared. So it looks like I've got 1 over y squared dy equals dx. Now, I'm going to give you a warning. I have seen this happen where people take anything that kind of looks like a fraction and decide it's natural log. That is wrong. What we have here is y to the negative 2. If it's a power that is not the negative 1 power, we can use the power rule. So the antiderivative over here, power gets bumped up by 1, multiply by the reciprocal to cancel. So this is sort of formally how it would look. Over here, antiderivative of 1 is x, and we need a plus c. We'll just put it on the right. So let's kind of make sense of this. This is negative 1 over y, if we simplify, is x plus c. So what does that mean? It means 1 over y is negative x plus c. So I negated this, but that the uncertainty absorbs it. So now c is just switch signs, but we still don't know what it is. If you want to put a minus here, that's fine. And so now y is the reciprocal of this. It's 1 over negative x plus c. And let me stress, it is not y equals 1 over negative x with a plus c at the end. The plus c at the end occurred when we took the integral. But in doing other steps, maybe that c moves around. Here I have 1 over y equals this thing. I am taking a reciprocal of the entire left-hand side and the entire right-hand side. So let's just be really clear about that. We do not just throw in a plus c. And what happens sometimes is people forget to put the plus c here, and then they get to the end and realize it should have been there, and they just throw it wherever they want to. Don't do that. Put it in once you do the antiderivatives, and then just follow where it goes based upon mathematical steps. So this is our general solution. To find our particular solution, we could say y of 0 would be 1 over negative x plus c, which is 3. So what does that mean? It means that 1 equals 3 times negative x plus c. 1 equals negative 3x plus 3c. Now here, we're literally solving for c, so don't do the 3 times c equals c trick. We want to actually solve for c. It's not, at this level, it's not an arbitrary constant. It's a constant that we're trying to find. Oh wait, but so x was 0. Yikes, yikes, yikes. I'm sorry about that. Let's redo this in a less idiotic way. I must be distracted. So this is negative 0 plus c. So we simplify, it's basically saying 1 over negative c equals 3. So if we cross multiply, 1 equals negative 3c, and c equals negative 1/3. So our particular solution for this one is y equals 1 over negative x plus negative 1/3. That's rather awkward, but I'll leave it as is. If you want to write it some other way, go ahead. And just one thing I'll point out is someone else, just as an aside, we had this. If you had said 1 over y is negative x minus c, then you would have y equals 1 over negative x minus c, which looks different. And then when you plugged in your particular, you would have y of 0 is 1 over 0 minus c equals 3. Wait. No, I'm so sorry. I messed up. I goofed here. So I really apologize. I threw in a minus by accident. Maybe you noticed that and we're starting to freak out. I really apologize. I don't know what I was thinking. Okay, so I found the general correctly. Now to find the particular. Y of 0, if I plug into this formula, is 1 over negative 0 plus c, which is 3, which is 1 over c equals 3, and c is positive 1/3. I don't know where that negative came from, and my particular solution would be y equals 1 over negative x plus 1/3, which is unsimplified, but that's okay. Now, I want you to realize that the choices you make about how to manipulate your arbitrary c will not affect your particular solution. So what could have happened, and you can just watch this, someone maybe was here and they negate each side to get 1 over y is negative x minus c. Right? They're just literally negating all of this, not trying to absorb the negative into c. So that person would say y equals 1 over negative x minus c. When that person tries to find the particular, they would say y of 0 is 1 over negative 0 minus c, which is equal to 3. So 1 over negative c equals 3, and they would get c equals negative 1/3. And you might think, well, Patrick, which one is correct? We did it before and got c was 1/3. Here we got c equals negative 1/3. But they're actually the same, because if over here in this example, the general solution was expressed that way, then when we plug in c equals negative 1/3, we would have y equals 1 over negative x minus negative 1/3, which works out to negative x plus 1/3, which is the same thing. So this will happen. Sometimes people will present their general solutions in different ways where the c's are not all labeling the same thing. That's okay. There doesn't have to be 100% universal agreement as to exact presentation of your general solution. You can still get to the same particular solution if you did things correctly. All right, let's take a look at this one. So here, if we cross multiply, we would get y dy equals negative x dx. Integral, 1/2 y squared equals negative 1/2 x squared plus c. For convenience, I'll multiply everything by 2. Y squared equals negative 1/2. Multiply everything by 2, so y squared equals negative x squared plus c. Doing that trick where 2 times c is still c. For reasons that may or may not be clear, I'm going to write this as c minus x squared. So y is plus or minus the square root of c minus x squared. That's my general. For my particular, I will now say y of 4 is plus or minus the square root of c minus 4 squared, and I want that to come out to 3. If I got 3, then I clearly took the positive square root and not the negative square root. So we have the positive square root of c minus 16 equals 3. Square each side, c minus 16 equals 9, and c equals 25. So our particular solution is that y equals the positive square root of 25 minus x squared. And something that you'll notice here, which is kind of nice, if you graph that function, what you get is the upper semicircle centered at the origin with a radius of 5. And if you're comfortable enough with the geometry involved, it should make sense that this actually describes what's going on a circle. So if I take some point here, right, let's not worry about that 4, 3. Actually, here, let's put it up here. That's not 4, 3. This is just some point A, B. Here's what we'll notice. This slope is B over A. Coming from the origin, that's just B over A. What is this tangent slope? The slope of the tangent. Well, let's think about this. Hopefully something you know about circles. Even if you never formally learned this, hopefully it feels right. This radius and this tangent are perpendicular. So if this slope is B over A, this slope is the opposite reciprocal. So what this is really saying is slope of the tangent is minus A over B, that's negative X over Y. This is the kind of thing that should be true about circles. So it's just kind of neat how that all fits together. Okay, so there's kind of a lot to digest here. This thing where you're doing separation of variables, you need to do it a lot of times. It's a simple process, but every single one has slight variations as to what do I do after I take the integrals? Am I taking square roots? Am I dealing with exponents and logs? And you want to go through various possibilities. If your log and exponent rules are weak, you want to discover that now so you can fix them. But I will